Hello, my name is Sawan Patwadom. I am a PhD student at Drexel University. Today, I am going to present our recent work titled SAT Attack Resilience Measure for Access Restricted Circuits, which I co-authored with Dr. Alvista Sasan and Dr. Yanis Savidis. Let's get started. With the recent development in logic locking on sequential circuits, a new type of hardware security technique emerges to protect the scan chain. These techniques aim to restrict usage of the circuit output rather than obfuscate the circuit design. These logic restriction techniques will be the topic of the presentation today. There are three main things that I will talk about. First, I will define what a logic restricted circuit is like. Next, I will talk about how to evaluate security strength of such a circuit. And third, we will take a look at some logic restriction schemes to illustrate that the design space for logic restriction is large and there is plenty of room for a new design. But first, we will have to do a quick review on the SAT attack and its resilience measure first. Logic locking on sequential circuits requires scan chain access to be protected. Otherwise, if the scan chain is accessible to for the attacker, the obfuscation can be reduced to that of a combinational circuit, which is easier to solve. One type of scan chain protection techniques is scan obfuscation, such as the technique called encrypt flip-flop, which ambiguously inverts the scan chain shifted values of the flip-flops along the chain. Another type of more recent techniques is scan chain access restriction, which works like a password authentication. The end users need to input external key pattern that matches the secret scan key value, which is preloaded onto the IC. If the external key is wrong, the scan enable signal is stuck low and the scan shift operation cannot be used. So this motivates the following questions that we will answer in this work. First, how can we evaluate the security of an access restricted circuit, such as the restricted scan chain? Second, is access restriction the same as logic obfuscation that we are more familiar with? And third, are there any other designs beyond the comparator stuck at zero design as the one shown on the right here? But before we get to those three main questions in the previous slide, we will first do a brief review on SAT attack and on one of the way that we can measure and report SAT resilience for a given obfuscated circuit. On the right here, we have an obfuscated circuit in the form of an extracted netlist, which is leaked from an untrusted partner on the supply chain or obtained with some reverse engineering technique. In the middle, we have an activated live IC bought from the market. The IP owner preloaded the correct key value K1, K2 of 10, which an attacker cannot read from the live IC because it is stored on a tamper-proof memory, the TPM. The output functionality of the activated live IC is the same as that of the original circuit and is referred to as the oracle. Given a pair of the oracle and the obfuscated netlist, FO and F, we can derive a truth table denoting whether the output pattern is uncorrupted or not, here denoted as a truth table U. A query to the oracle for a given input pattern yields an input-output pair observation, which can help eliminate some incorrect key columns. A sufficient correction of input-output pairs will remove all incorrect key columns, and there are many possible sufficient sets that we can choose from. The set can be constructed efficiently by iteratively picking a new input patterns that will remove at least one new incorrect column. Such an input is called a distinguishing input pattern or DIP, and such an algorithm is called the SAT attack. The flowchart is shown here, though we don't have time to go over. The key point is that the time to solve can be used as a resilience measure, and the total time is proportional to the number of iterations, lambda, which is the same value as the number of dips used. One way to report the value of lambda is to first model SAT attack search paths as a random process. For a given user table, which can be viewed as a search space itself, we can enumerate all the possible search paths and visualize them as dip sequence 3 as shown here. Assuming some branching probability, such as equally likely, we can compute the probability of such attack execution, taking any given path on the tree. Each value in blue at the bottom is a product of the red values along the path. Finally, summing all the probabilities of the outcomes with the same search path length, we get the probability of lambda equals to that value. So let the random variable d denote lambda. We can then derive the probability mass function PMF of d along with its statistics. In summary, for a given user space, we can derive the means and the other statistics. With such attack resilience measure reviewed, we can then move on to distinguish logic restriction from obfuscation. Here we can classify techniques based on usability of the output with respect to the end user. In the first column, the output is readily usable. In the top row, we have a regular logic obfuscated circuit. Note that the values in the tamper-proof memory, the TPM, is already loaded. In the bottom, we have an original unobfuscated circuit. In the second column, the output is not usable yet. Until it is restored via pre or post-processing, either in hardware or software, similar to an encryption scheme. This can be viewed as functionality restriction via encryption. Finally, in the third column, the correctness of the output is undetermined because it depends on the external key inputs, which are to be configured later by the end user. So using this classification system, the scan chain protection techniques from earlier can be classified as shown. The new type of hardware defense techniques that require attention here is the third one on the one on the third column. First, let us take a look into some deobfuscation examples. Given this toy example, here we have two correct key patterns. Consider these four different attack scenarios where the scenarios A and B, we have the same logic obfuscated circuits, but with different attackers. Next, consider scenarios C and D, which are attacks on logic restricted circuits. With the scenario D here have a key gate and a camouflage gate mixing in along with the external keys. Nonetheless, all four scenarios here have the exact same two correct key patterns. Now, let's consider two different attackers. For the blue attackers, A, M, and F, who wants to modify at fabrication time and replace all the key gates and camouflage gates with some standard components, such as buff or NOT gate or wire, versus the red attacker, AUOP, who wants to unlock an overproduced obfuscated IC, which is bought from the black market. The live IC here is not yet activated. So the red attacker wants to load the correct key value to the tamper-proof memory, the TPM. However, there is a complication because the value of KA TPMs depends on the value of KB camo. The red attackers need to perform some extra steps to resolve KB, whereas the blue attacker on the left does not have to. So here we have exact same obfuscated circuit, but the deobfuscation process plays out differently for the two attackers. This is due to the presence of some unchangeable secret key. For the red attacker, KB camo is unchangeable, but for the blue attacker, KB camo is changeable. Next, let's consider scenarios with the same attacker, but two different logic restricted circuits, C and D. On the left, all key signals are external inputs, whereas on the right, there is a key gate and a camouflage gate mixed in. An end user attacker AEU wants to input correct external key values. On the left, the attacker can pick KA, KB to be either 0, 1 or 1, 0. However, on the right, KA externals need to be selected accordingly, depends on the internal KB TPM. Similar to what we have before, we need some extra steps for the scenario on the right, but not for the scenario on the left. This again is due to the presence of some unchangeable secret keys, which depend on the attacker capabilities of the scenario. So we have two types of the obfuscation scenarios. On the left, we have a regular set attack, whereas on the right, we have a situation where a regular set attack alone is not enough. From scenario C, we can observe that having external keys alone is not the cause of the special situation. So the obfuscating logic restricted circuit is not always different from the obfuscating logic obfuscated one. However, the presence of the unchangeable circuit keys does make a difference. So let's define the control key as KC in green and define the uncontrollable unchangeable key as KU in purple. So here we have two types of the obfuscation problems, the one with KC alone and the one with both KC and KU. The one with KU requires formulation of new attacks and security evaluations. And these scenarios occur naturally in logic restricted circuits with logic locking and or IC camouflaging. For example, in the scan chain restriction from earlier. Next, we will talk about the security evaluation framework. First, let's formulate an attack where the goal is to find the correct external controllable key KC. In order to activate the restricted live IC as shown here, we will need three components. Note that the values loaded onto the TPM do not have to be the same if there are multiple correct keys. The first two components form the usual pair of the regular set attack, denoted here as function FO and F. Here we can find the correct key patterns of the KU-KC vector. In this example, we have 4 correct key patterns where we cannot pick KC yet because KC depends on KU. So to gather more information, we can interpret the extracted netlist as a new function, H, where KC is now lumped together as a primary input vector, leaving KU alone as the key. The H truth table is then simply a new arrangement of the OF table as shown in these highlighted colors. The oracle HO is simply the restricted live IC itself, here with the secret KU being KTK4 equals to 1, 0. The pair H and HO then forms another set attack, which allows us to find the correct KU. After the two set attacks, we now know KU is 1, 0 for this restricted live IC, which allow us to then pick the corresponding KC of matching value. In summary, the attack is to apply set attack twice, thus called two-stage set attack. We can either solve UF space first, then UH, or the other way around. However, the order does affect the obfuscation efforts. If we can early conclude KC, the second stage set attack on UH can then be skipped. Next is if we apply the key space constraint learned from the set attack in the first stage, the new search spaces at the second stage are possibly smaller and are denoted here as UH prime and UF prime. An example of early conclusion is when there is only one correct KC-KU, so KC can be picked right away. Thus, the second stage set attack on UH is not needed. In the next example, we move KA down next to KB. As a result, there are now two correct KC-KU patterns. However, since KU is unique and KC does not depend on KU, KC again can be picked right away, any of the two. In circuit example 3, KB is now changed to TPM and KC is now external. Basically, we swap the two key signals. In this scenario, we cannot pick KC yet because KC depends on KU. However, we can still apply key space constraint learned for the first stage. By keeping only the columns with KU matching the correct values from stage 1, some other columns can then be removed, resulting in a smaller subspace UH prime. Similarly, we can do the same thing with UF prime space, keeping only the subspace with correct KU. The new space UF prime is smaller and is easier to solve, or at least equally hard, as can be seen from the smaller expected number of dips, ED value. Similarly, the reduced search space UH prime is also possibly smaller, although in some cases, UH prime can be the same as UH, which we will see in the next section. Now, we are ready to formulate the set resilience measure of a logic restricted circuit, which is approximately the combined time to solve of the two set attacks. Because there are two possible orders on which search space got attacked first, the time to solve is then taken as the minimum of the two. In this work, we compare and report the scaling factor, the expected number of dips, ED. In the next section, we will use the two-stage set attack to evaluate and compare set resilience of two different logic restriction schemes, while also exploring logic restriction design space. The goal here is to explore other logic restriction schemes beyond the comparator-based one shown in figure A. As an example, we can borrow technique from logic obfuscation, such as SALock, to make a logic restriction version shown in B. A circuit locked with the original SALock is shown here on the bottom. To convert it as a logic restricted circuit, K1, K2 is now changed to be external inputs. In the original SALock, the correct K1, K2 has to match the flip exception, which is hard-coded in the netlist. Here, we configure the exception value with the XNOR key gates instead. As a result, we get a logic restriction as shown in B, which then has a flip exception controlled by the value of K3, K4. Thus now, the correct external K1, K2 has to match the secret K3, K4, which is preloaded onto the TPM. Both circuits A and B have multiple correct key patterns for all possible KU values and KC depending on KU in one-to-one manner. Because KU spans all possible values, it can be chosen arbitrarily, and this serves well as a personal key for each restricted live IC. For a visual comparison, the search spaces for the two circuits are shown side by side. Here we can see that UH prime search space is not smaller and is the same as UH because the correct KU spans all the possible values. Thus, no columns can be eliminated. Next, we can see that UH space reflects the brute force behavior of password guessing as expected. If the correct password is guessed, the process is completed. All other wrong passwords are ruled out. Whereas if a wrong password is guessed, only one candidate is ruled out. Finally, we can observe that in the comparator-based design in figure A, UF search space is weak and underutilized. On the other hand, it can have higher corruption per columns, which depends on the original function FO. Finally, let's summarize the key takeaways. In this work, logic restriction is defined as a new class of defense techniques, which is when a circuit is logic locked with some unconfigured keys. Second, a new deobfuscation problem emerges when uncontrollable key KU is included. Third, two-stage set attack is proposed as a framework for measuring resilience of a logic restricted circuit. Finally, to illustrate the large design space of logic restriction, SALock-based logic restriction scheme is shown as an example and compared against the comparator-based design. Thank you for attending my presentation.